What we're going to talk about in section 5.5 today is the real zeros of polynomial functions. We need to start out by talking about what we call the division algorithm. Algorithm just means a series of steps. So what we're doing is we are going to be dividing two polynomial functions. So the numerator is going to be the dividend. The denominator is going to be the divisor. And when we do our division problem, we're going to end up with a quotient, which is the top row when you do division, long division. Then we're going to add the remainder that we get from long division over the divisor. So basically what we're going to be doing is we're going to have f of x inside our division symbol. G of x is going to be the thing we're dividing into f of x. We end up with q of x as our quotient. And when we get all the way to the end, down at the bottom is our remainder. Okay, another way to rewrite one of these functions that we have by division is if I multiply each term by g of x, then we would have f of x equals q of x, which was the quotient. So we could rewrite our function as the quotient times the divisor plus the remainder. So we will see these things written most frequently in this format, where we take the quotient times the divisor plus the remainder, and we'll use this to simplify polynomial functions throughout this chapter. Now, if you're lucky and your divisor is linear, then you can do something called synthetic division. So when I say the divisor must be linear, what that means is it can't have any squared terms. So it would have to be like 5x plus 2 or x minus 3, but it could not be something like 5x squared plus 2. Okay. The divisor is the thing we're dividing by. When you do synthetic division, you have to use space holders if you have any missing terms, all the way down to the constant term. Well, that m got really small. That's weird. So here's going to be an example that we can do by synthetic division. You could do this by long division, but I'm going to tell you that synthetic division is like 20 billion times faster, and you're way less likely to make mistakes. So if you remember what we were doing in section 5.3, we had to do polynomial long division. This time, if you can use synthetic division, it's so much easier. So in synthetic division, I won't write out the steps because it's very, very hard to write out the steps, but it's really easy to do and to demonstrate. So in synthetic division, you're just going to take the coefficients from the dividend row. So I just use 5, 18, 7, and negative 6. I did not have any missing terms because it went x cubed, x squared, x, constant term. If I had any missing terms, I would have to put zeros in them. And then I put a little box over here on the edge. I'm going to leave a space for a row here and draw a line with a box around this bottom right-hand side. When I get finished doing my synthetic division, this row down here is going to be the quotient. This in this little box on the side is going to be the remainder. So what I'm going to put into this little box here has to do with my divisor, but I have to get what x equals. So I'm going to take x plus 2 equals 0, and then I subtract 2 from both sides. I get x equals negative 2. So what goes in that box is negative 2. Now to work through synthetic division, what we're going to do is you're going to drop this first term straight down to here. So that's going to be a 5. Always your first number just drops straight down. And then you're going to take that 5 and you're going to multiply it by the -2 that's in the box up there. So I'm going to do 5 times -2. That's going to give me -10. And then I'm just going to add straight down. 18 plus -10 would give me 8. And then I'm going to multiply again times -2. -2 times 8 will be -16. Then I'm going to add these two numbers straight down. I get -9. And then I'm going to multiply again times -2. And I get +18. And then I add those together and I get 12. So we could rewrite this little dude here, that original division problem. We could rewrite it as the quotient plus the remainder over the divisor. So if I rewrite it as the quotient plus the remainder over the divisor. The quotient row is this row, 5, 8, -9. But we have to put the variables back on, okay? So the way that that's going to work is we're starting with 5x cubed and we're dividing it by x. So what's going to happen is every variable is going to be 1 less degree. So instead of starting with x cubed, I'm going to start with x squared. So my quotient would be 5x squared plus 8x minus 9. So whatever your dividend was, then your quotient will be 1 degree less, and then it will just go down by 1 each time. The remainder is just going to be the number 12. And the divisor is the original divisor for the problem, so it'll be x plus 2. Sometimes it will ask you to rewrite it in that format, and sometimes we will be using this same process, but to try to factor a polynomial function down to its smallest mabobber thing. Okay, the other thing we can do with synthetic division is we can use what's called the remainder theorem. The steps are the same. The remainder theorem says when you do synthetic division with some number up in that box, then when you get to the end, the remainder would be f of c. So it's called synthetic substitution because it gives you the same number that you would get if you did substitution, but you're using the process of synthetic division. So if I look back to that problem that we just did, by the remainder theorem, this would show that f of -2 would equal 12. So in other words, if f of x was 5x cubed plus 18x squared plus 7x minus 6, that's this row, 5x cubed, 18x squared, 7x minus 6, and I substituted in -2, and what I got out was 12. So the remainder theorem is a little handy to do a couple of things. One, this also gives me an ordered pair. F of -2 equals 12 gives me the ordered pair. -2, 12. And what we're really going to use this to capitalize on is being able to find roots. Because remember, roots are another word for x-intercepts or zeros. And in an x-intercept or a zero, what we're looking for is for this y value to be 0, because that's what x-intercepts do. So that's actually where we're headed on our next page about the factor theorem. The factor theorem says if the remainder is equal to 0, then the divisor is a root or 0 or x-intercept. Remember, those things are all synonyms. So in other words, if f of c equals 0, then x minus c is a factor of f of x. And if x minus c is a factor of f of x, then f of c equals 0. So basically, if I do f of x divided by x minus c, then what I would have in the box here, remember I would set x minus c equal to 0. So what goes in the box would be c. Then I'd have the coefficients of f of x up here. And if I end up with a 0 in the remainder, then that means, bless you, that C0 is on the graph and C0 is an x-intercept. That also means that x minus c is a factor of f of x. So we can use that to break down big polynomials into smaller polynomials and then eventually get a fully factored polynomial where we couldn't use regular factoring techniques in the past. Okay. So what I want to do on this example is first, I want to evaluate f of x for x equals 5. In other words, I want to find f of 5, and then I want to decide if 5 would be a root of that polynomial. So to find f of 5, I'm going to use synthetic substitution. So I'm going to put 5 in the upper left box. And when I get finished, this remainder down here is going to tell me what f of 5 would be. So I need to put my coefficient row up on the top here. So I will start with a 4. And then negative 16 on the x cubed, and then 7 on the x squared. And then I need a 0 because I am missing an x term. So I have to use that 0 as a space holder, and then 20 for my constant term. Then we just run through the synthetic division. So remember, this 4 always just drops down. So that'll be a 4. And then we'll do 4 times 5, which will give me 20. And then I'll add negative 16 and 20, gives me 4 again. And then multiply the 4 times 5, which again gives me 20. Add the 20 and 7, 27. Multiply the 27 times 5, which is 135. Add straight down, 0 plus 135 would be 135. And then multiply the 5 times the 135, which is 675. And then I add straight down, so I get 695. So what I get at the end, the remainder, is f of 5. So f of 5 would equal 695. So then if I asked, is x equals 5 a root? No, because the remainder does not equal 0. Okay, on the next example, we are going to determine if the given value is a root. If it is, then we're going to find all of the other zeros for f of x. So to determine if it's a root, we're going to use synthetic substitution. So we'll put 2 in the box, and then we're going to put our coefficients on this row. So the coefficient of x cubed is 1. Then the coefficient of x squared is 0 because it's missing. And then for the coefficient of x, negative 7. And then the constant term is 6. Draw our box so that we just remember that that's a remainder. I don't think that everyone who does synthetic substitution puts that box around the remainder, but it helps me keep track of it to make sure that I'm like aware that it's a special number. So we'll run through synthetic division. The 1 drops down. 1 times 2 will be 2. Add the 0 and 2, we get 2. 2 times 2 will give me 4. Add straight down, negative 3. 2 times negative 3, negative 6. Add straight down, and we get 0. Bless you. So what that means is that x equals 2 is a root, or x-intercept. Oh, that's a weird dash. X-intercept. Bless you. And that also means that x minus 2 is a factor of f of x. So here's where that stuff that we talked about on the first page comes into play, where we can rewrite it. F of x can be rewritten as the quotient times the divisor plus the remainder. Since our remainder was 0, then we won't have a remainder to write down. So we will rewrite our function as the quotient times the divisor plus the remainder. So f of x is now going to be, remember in your quotient row that our function started out degree 3, and so it's going to be 1 degree lower. So we're going to start out with x squared. So it'll be x squared plus 2x minus 3. And then the divisor is going to be that factor. So we don't just put a 2 in there. We know that that was x equals 2. X equals 2 is the root. So we move the 2 back over with the x to get x minus 2 to be our factor. And then the remainder is 0. Okay. So we don't really have to write the remainder because it's just 0. And then we look at what we have left. This dude right here is a quadratic. So we can actually just factor it. So we'd rewrite f of x as x squared plus 2x minus 3 factors to x plus 3 times x minus 1. And then we keep the x minus 2 that we had before. And now this is in what we call fully factored form. We'll talk about that more later on in this section as well. It's in fully factored form, but what it wanted us to do was find all the zeros. And the way that we find all of the zeros is by using that zero product property. So we take each of these parentheses and set them equal to 0, because when we find x-intercepts, that's what we do. You set the equation equal to 0 and then you solve it. So we'd have x plus 3 equals 0, x minus 1 equals 0, x minus 2 equals 0. So all of our zeros would be -3, 1, and 2. All right. Now that's all good and fine if they tell you what number to check to see if it's a root, but how do you have any idea what numbers to check? Because you can't just be checking randomly like 1,000 different numbers. So we have something that's called the rational root theorem that helps us know what numbers would be a good number to check to see if it's a root. So here's the rational root theorem. It says that rational roots, okay, remember rational numbers? Rational numbers are things like, rational numbers are fractions and integers, basically. What they don't include are imaginary numbers and radicals. So imaginary numbers like 2 plus 3i and its conjugate 2 minus 3i, or rational numbers like 2 plus square root of 3 over 7 and its conjugate 2 minus square root of 3 over 7. Bless you. We'll talk more about conjugates a lot later on. A good thing to keep in mind for now is that anytime you have an imaginary root, you're going to guaranteed have 2 of them because they always go in those conjugate pairs. Same thing with radical. If you have an irrational root, they will always show up in pairs as well, and they'll be conjugates. I guess I should have put irrationals instead of radicals. Because rational roots are these kind, irrational roots are the ones with the radicals, and then also the imaginary numbers. are not included in this. So rational roots can only occur at values found in the list created by listing the factors of the constant term over the factors of the leading coefficient. And then you have to split the list. I'll show you what I mean by that now. So, I guess I have that written here. So find all the roots of a polynomial function. The way that we start to find all roots, the way that we start is by listing the possible rational roots. Then after we find that list, we're going to test possible roots using synthetic division. And what we're looking for is to get a remainder of 0. Then we're going to rewrite our function as the quotient times the divisor. And then we repeat those first 3 steps, list, test, rewrite, until you have a quadratic. And then you can factor or complete the square or quadratic formula to find the last 2 roots. Okay. So we'll get a lot of practice doing those steps. And we're going to start with this function that's up at the top, 3x to the 4th minus 23x cubed plus 19x squared plus 27x plus 6. Okay, to begin this, we're going to do the factors of the constant term, which is 6. So we need factors of 6 over factors of the leading coefficient, which is 3. So factors mean the numbers that multiply to give you. So the factors of 6 would be positive and negative 1, 2, 3, and 6. Because I could have 1 times 6 or 2 times 3. And then the factors of the leading coefficient would be 1 and 3. Now, what I mean when I say split this to create the list is basically you're just going to go one at a time along the denominators. And so I'm going to forget about all the other denominators, and I'm going to write each numerator using the denominator of 1. So I will have plus or minus 1 over 1, which is 1, plus or minus 2 over 1, which is 2, plus or minus 3 over 1, which is 3, plus or minus 6 over 1, which is 6. And then I move on to the next denominator, and I do the same thing. So I'll need plus or minus 1 over 3, which is a fraction, and then plus or minus 2 over 3. Now, when I get to doing 3 over 3, 3 over 3 would simplify to 1, and I already have 1 on my list, so I don't write that again. And then 6 over 3 would be 2, and I already have 2 on my list, so I don't need to write that. So altogether, I have 2, 4, 6, 8, 10, 12. There's 12 possible rational roots. So the most number that I would have to check would be 12. If you're really unlucky, you might have to check through 12 of those, but hopefully that won't happen to you. Then we want to decide how many roots there will be using the degree of the polynomial. So how many roots are we looking for in this one? We'd be looking for 4. A lot of times when I'm doing these problems, then I just go ahead and write 4 x equals is. So once I fill in all 4 of those roots, I know that I'm done with the problem. And then this part I like to do with a pencil because I often have to redo it a number of times because I'm not really good at getting it on the first guess. So what we're going to do for this process is we're going to pick a number to test using our function. So we'll use synthetic division because it's faster. So we'll do 3, negative 23, 19, 27, and 6. And what I'm trying to do is get a remainder of 0. So I'll start with, I'll try 1. So 3 drops down. 3 times 1 will be 3. Add, negative 20, multiply, negative 20, add, negative 1, multiply, negative 1, add 26, multiply 26. And if I add those, I get 32, which, I mean, I guess that's helpful. That tells me that I have an ordered pair 132 on my graph, but it's not a root, so I have to go again. So I'll try 2. So I do 3, negative 23, 19, 27, 6. So the 3 drops straight down. We get 3. Then 3 times 2, we get 6. Then add straight down, negative 17. Multiply again, negative 34. Add straight down, negative 15. Multiply, negative 30. Add straight down, negative 3. Multiply, negative 6. Add straight down, 0. So x equals 2 is my first root. So I go ahead and put that in my list up there. And then I'm going to rewrite my function as the quotient times the divisor. So I will have f of x equals, now the quotient, remember my function started out being a 4th degree, but each time I divide it, it gets 1 less. So now it's going to be cubed. So it'll be 3x cubed minus 17x squared minus 15x minus 3. And then it'll be times x minus 2, because that's what I've divided out. And I'm going to go through that entire process again. So starting back at step 1, which is list, and then I'll test, and then I'll rewrite. But what I want to do is use the quotient. So I'm going to use what they call the depressed function, because it's 1 degree lower. I'm going to use this smaller function to do my list, test, and rewrite. So on my list, I need factors of the constant term, which is 3, over factors of the leading coefficient, which is also 3. So I'll have plus and minus 1 and 3 over 1 and 3. When I split that list, I'll have 1 over 1, so plus or minus 1, and 3 over 1, plus or minus 3. And then 1 over 3, so plus or minus 1/3, and then 3 over 3, which is 1. So I won't rewrite that one again because I already have it on there. Now, we've already tested 1 up here. So here's the thing. If you test it in the first one and it doesn't work, it's also not going to work in the second one. But if you test it in the first one and it does work, it might work a second time. But since we've already tried 1 up here, it's not going to work in this other one. It didn't work the first time. It's not going to work the second time. I will just kind of save us the suspense and say, let's try testing negative 1/3. Ooh, wait, I have space to do this in. I left more space here. The next page, it's going to continue to the next page, but I have room here. So let's try negative 1/3. I don't want you to be scared of using fractions in these. They actually don't end up being really disgusting. So we'll start with this row since we're working with the 3x cubed. So we'll do 3, negative 17, negative 15, negative 3. Usually kind of what happens is if your fractions, when you do division with a fraction and it starts coming out gross, it's probably not a root. Because if it comes out nice, if it works, it usually comes out nice. If it starts coming out really nasty, probably not a root. So again, we bring that 3 straight down. And then 3 times negative 1/3 would be negative 1. Then we add straight down. We get negative 18. Negative 18 times negative 1/3 would be 6. Add straight down. Negative 15 plus 6 is negative 9. Negative 9 times negative 1/3 would be 3. And then 3 plus negative 3 would be 0. So my next root that I'm putting on my list is negative 1/3. So I'm going back to my roots list and writing negative 1/3 as my second root. So that was my test step. After I list and test, then I'm going to rewrite. So I'm going to rewrite my function as the quotient times the divisor. So the quotient would be 3, bring it down a degree, x squared, minus 18x minus 9. And my divisor, since I divided by negative 1/3, that means x equals negative 1/3. So I add the 1/3 over to get x plus 1/3 equals 0. The x plus 1/3 is my factor, so x plus 1/3. And then don't forget the x minus 2 that was on there from the last time. So times x minus 2. Okay, now I have to show you a very weird thing that happens. Like, I'm aware that this is totally weird. Whenever you get a fraction-y root next to a factor that has a GCF, you have to do this weird thing. The GCF for this group would be 3. So what I'm going to do is I'm going to rewrite this. I'm going to take the 3 out of this group. So that's going to leave x squared minus 6x minus 3 times 3. And then I still have times x plus 1/3 times x minus 2. So now that I've taken the GCF out of the first parenthesis, what I want to do is give it to this parenthesis, because then that parenthesis doesn't have to have fractions, and that's nice. So we'll have f of x equals, this guy still says x squared minus 6x minus 3. But now I'm going to multiply this 3 into this parenthesis. So that's going to give me 3x plus 1 times x minus 2. If I were to set 3x plus 1 equal to 0, I would still get x equals negative 1/3, which is the root that I found. So we haven't changed anything. We just did a little bit of rearranging. Now we repeat those steps, list, test, rewrite, list, test, rewrite, list, test, rewrite, until what happens? Until we have a quadratic quotient. So if you look at our quotient now, this little dude is a quadratic. So once this is a quadratic, at that point, we can either factor it or complete the square or quadratic formula. Okay. Spoiler alert, this one does not factor, so we will either need to complete the square or quadratic formula. I think I hear people wanting to complete the square. Quadratic formula? Yep. Okay. So if we quadratic formula it, we'll do x equals the opposite of b, so positive 6, plus or minus the square root of b squared, so 36, minus 4 times a, which is 1, times c, which is negative 3, all over 2 times a, which is 1. So x will be 6 plus or minus the square root of something over 2. So this is going to be 36 and then plus 12, so 48. 48 breaks down to 4 times 12, which would be 4 times 3. So x would be 6 plus or minus. I can take the 4's out. So 6 plus or minus 4 square roots of 3 all over 2. And then because each of my coefficients is divisible by 2, I need to do that. So x would be 3 plus or minus 2 square roots of 3. Those are my last two roots. I get x equals 3 plus 2 square roots of 3, and x equals 3 minus 2 square roots of 3. And just like I told you, if you get radicals, if you get irrational answers, then there will always be two of them, and they'll be conjugate pairs. So I have found all my roots, which were 4. But I want you to know that you may be asked to find all the roots, which we just did. So in our case, finding all the roots would be x equals 2, x equals negative 1/3, x equals 3 plus 2 square roots of 3, x equals 3 minus 2 square roots of 3. So if they ask us to find all the roots, that's it. We just have to list them out. But they also may ask us to write it in fully factored form. Fully factored form means I would have to have as many parentheses as I have roots when I put them back together. So the x equals 2 is easy. So in fully factored form, x equals 2. Remember, you subtract the 2 over. So I'd have x minus 2 in that parenthesis. For x equals negative 1/3, remember that's the one that we had to make look weird. We had to take the 3 out and put it back in. So instead of writing x plus 1/3, we would want to write it as 3x plus 1. So 3x plus 1 is our second one. And then on these last two that are irrational, basically you're just going to add and subtract both of the terms over to the other side. So it'll be x minus 3 minus 2 square roots of 3, because we want to get it equal 0. So x minus 3 minus 2 square roots of 3 for one of them. And then on this one, we would have to subtract the 3, but add the 2 square roots of 3. So x minus 3 plus 2 square roots of 3. And that would be that polynomial in what we call fully factored form.